In this session, we are going to learn about analysis of portal frames using moment distribution method. This is done for two different situations. First one is portal frames without side sway, and in this case the analysis is done in same way as we did for beams, and the side sway may not be there because of two reasons. First is if frame is geometrically symmetric and they have symmetric loading, and second situation is if side sway is restricted using some support. So if we look at the two situations, the first situation is the beam is symmetric geometrically as well as the loading is also symmetric, so there will be no side sway. In the second case, we have beam which is unsymmetric geometrically and the loading is also unsymmetric. So if the support were not there at point C, then there will be side sway, but because we have provided one hinge support at C, there will be no side sway. So this case can also be solved using moment distribution method for beams. Second case is when frames have side sway. Such frames are solved using principle of superposition, and in solving such frames we divide the frame into two cases. In case 1, we apply a support at the joint. In this case we apply a support at joint C so that side sway is restricted. But because we apply the joint at C, the result will not be same as the result for given structure, and to compensate that we add case 2 to that, and in the case 2 we do not apply any external load, but we apply a load at joint C, and the value of load R dash should be equal in magnitude to the support reaction at C and opposite in direction to reaction at support C. So our R dash should be equals to R, and I have shown R and R dash in opposite direction. So sum of case 2 and case 1 will give us result for given structure. Now to solve case 1 and case 2, case 1, because there is no side sway, the case 1 can be solved the way we solve beams, and we can find n moments and we can also find n shears, and using those n moments and n shears we can draw free body diagram of entire frame and find support reaction R at support C. In case 2 we consider only side sway because of force R dash at C, but because R dash is acting at the end of the member, this will have no contribution towards fixed end moments, but we know that in this case there will be side sway, so we can write fixed end moments in terms of side sway. So if delta is the side sway of our structure, then for each beam segment we can write fixed end moment for near and far end using minus 6 EI delta upon L square. Now each member may have different EI and L, so the fixed end moment for each segment will have different numerical value, and we have to be careful here that delta is the downward displacement, and downward we mean perpendicular to the axis. So for example, for segment AB the delta will be actually horizontal in the right side, not downward. But if I look at my segment AB from this side, then B end is going downward with respect to A, and if I look at segment BC from this side, then in this case both end B and C are moving horizontally, so there is no displacement or there is no relative displacement of C with respect to B perpendicular to the axis of segment BC. So for BC, delta will be 0, and for CD, delta will be delta. Now once we write fixed end moments for all segments in terms of their corresponding E, I, delta and L, we assign numerical value to one of the minus 6 EI delta upon L square, and with that assumed value we can find numerical value for n moments of all the segments. Once we have all the n moments, we can do moment distribution method and find n moments for all the segments, and we also find n shears for segment AB and CD at points or at ends A and D. Now once we have all the n moments and these n shears, we can write equilibrium in case 2 for entire frame and find numerical value for R dash. So here the n moments that we have obtained in case 2, they correspond to this numerical value of R dash. Now in 99.99% cases, this R dash will not be equal to R of case 1. So to obtain the corrected n moments, we have to scale the n moments for R, and the scaling is done using this formula where MR will be equals to R upon R dash into MR dash. So in case 2, the scaled n moments will be MR equals to R upon R dash into MR dash. Once we have the scaled moments for case 2, we can find the n moments for given case by adding the n moments for case 1 and case 2.